Hey everyone, it's Dr. Calkins, week 14, chapter 9, Stoichiometry, spelling word of the day. What's most important about stoichiometry is it's a calculation of how much. So lots of occupations have how much in their job descriptions. If you're a plumber or some kind of contractor, what you need to know is how much pipe, how much glue, how many boards if you're a home builder. Even if you work at Hardee's, you need to know how many stacks of cheese go on a Whopper or a cheeseburger, whatever. So in that situation, it's no different in chemistry because you have all these ingredients and some things likely to run out first. So we can use calculations to know how much to use and how much not to waste, that kind of idea. So lots of definitions in this chapter. The most important definitions that we're going to talk about is our number. So in stoichiometry, what's important is to know our number. If you're a baker, your number is a dozen. That's just how you say the word, in this case the number 12, over and over and over again in your occupation. For a chemist, it's the same idea but much fancier. We use a mole. So it's the same context of it's just a number we use all the time, so it's easier to say mole than the actual number itself. Is it really that much harder to say 12 for a dozen? Probably not. But in chemistry, our mole is 6.02 times 10 to the 23rd, so we have 3, 6, 9, 12, 15, 18, 21. So here's 3, 6, 9, 12, 15, 18, 21, 22, 23. So there's our 6.02 times 10 to the 23rd power as a number. Barely fits on my little screen. If we were to win $1 million, you'd put a 1 here. So that'd be at this position here. That's the millionth place. Here we have the billions. Here, if we put in like 30, that's how broke the United States is after the coronavirus, probably. In the trillions of dollars, who knows what that number really is. But even on past that, we have trillions upon trillions, and instead of even thinking about how big this number is, we just say that's 1 mole, because it's easier to think about a brown furry creature instead of this big crazy number. So when we use a mole, we also think, and this is called Avogadro's number. He's the one that estimated, and this is a huge estimate, it's estimated to this position. It's a huge estimate of how many atoms are in a mole or how many molecules are in a mole. To give you some context of how big Avogadro's number is, if you had Avogadro's number of softballs, it would be the size of the Earth. From here to China to back around, from North Pole to South Pole back around, if you stack softballs side by side by side, you'd have something as large as our planet. That's how big this number is. If you had this many shot put balls, it would be as heavy as the Earth. So it's a huge number. And it's such a large number that it's so hard to even think about how big this number is. It's easier just to say that's a mole. Just like 12 donuts is a dozen for a baker. So don't get too worried about this number. Just know that it's a huge number. It's how we relate things that are 1 millionth the size of a piece of hair called atoms and something meaningful that we can see on a balance eventually. So another definition that's going to come up is how we can relate a mole. 1 mole is also grams on the periodic table. So when we look at the periodic table, you're going to have the atomic number up top, you're going to have the symbol, then you're going to have this number on the bottom. That's the one we want. This can now be grams if we assume Avogadro's number of atoms are being counted. We're not going to say this number over and over again. We're just going to say mole because it's easier to think about. So when you look at this definition, it's grams per mole, basically per Avogadro's number of those individual atoms. So those are the 2 major definitions of this chapter. The only other mole definitions that we're going to have is when we have equations. We can have, say, A plus B goes to C. Now when you balance an equation like this, and let's just use like 1s, 2s, and 3s, these numbers can also be moles. It's really just saying that it takes 1 mole of A and 2 moles of B to make 3 moles of C. So these are what we would consider a mole ratio. So we could write that of 1 mole of A convert it to 1 mole of B, in this case 2, because that's a 2 moles of B. So we can use those numbers to convert, just like we can use grams and moles to convert, that's a conversion. Just like we can use Avogadro's number to convert, it would be 1 mole per 6.02 times 10 to the 23 atoms or molecules. So those are the conversions, either this conversion, where this is a 1, this is from the periodic table, or this is from some balanced chemical equation. That's really the 3 major ideas of this chapter. So let's write those in a slightly prettier form, and then maybe try a problem using them. So the first definition is 1 mole is equal to Avogadro's number. Huge number, and it could be atoms, it could be molecules, it could be formula units if it were a compound or something like that. Second definition is 1 mole is also grams from the periodic table. So we have 118 choices there, or we can add them up for larger molecules or compounds. And then now we know that you can have a mole to mole ratio. Specifically, you're going to see that with coefficients, and that's from a balanced chemical equation. So you're going to use those large numbers in front. Something we didn't mention, but it's a little more no duh, you can also use subscripts. Rarely do we use this, but it is something that shows up in the PowerPoint notes a little bit, and that's when you have a chemical formula. So an example there, because we didn't give one earlier, if you had something like H2O, you could say there are 2 moles of hydrogen atoms per 1 mole of water molecules. And what we're saying there is really just look at the subscript. You can see how many atoms are in 1 whole molecule. So for every 1 molecule, how many atoms? That's a way to use subscripts, but again, it's not one that's used very often at all. In reality, these 3 definitions here will get you through the entire homework. To know that Avogadro's number is how we use the periodic table. So notice we have to go through a mole before we can go to grams. So if you want to go to grams to atoms, you have to go through a mole, so that's 2 conversions. Atoms back, 2 conversions. The only time we're going to use a mole to mole ratio is going to be when there's a balanced chemical equation. That's kind of midway through your homework. So let's try a couple example problems, and then this lecture is over. We'll talk about molecular formula in a separate lecture. So let's say we have a generic, let's try to keep these definitions in there. Generic reaction of hydrogen plus oxygen gives us water. So we need to balance this equation, because then we can use mole ratios, among other things. So if there's 2 hydrogens, that's good. There's 2 oxygens, there's 1 oxygen, so we need to double it. When we double this, we'll also double the number of hydrogens, so we need a 2 there as well in order to be balanced. So now we have a balanced chemical equation, which is what we need. If a problem, we're going to say you have, let's say 10 grams of water. How much oxygen or hydrogen is needed could be a potential problem. They could just say, how many moles of water do you have? So it's very similar to a homework question that we saw in our previous chapter with copper. If we have 10 grams of water, we can use grams from the periodic table to go to moles. That's using this definition here. This would be H plus O. And in order to do that, we need to go to the periodic table to get that masses. And just for example's sake, oxygen is about 16, hydrogen is about 1, so it's 1 plus 1 plus 16. So it's about 18.02 because hydrogen is 1.01, and that's close enough. If you take 10 and divide it by 18, you get the answer for a question like this. It's 10.0 divided by 18.02. So again, it's about half of 20, so it's about half of a mole. 0.366 there, so 0.555 moles. So this problem's pretty common. Notice grams cancel like they should, just like meter, liter, grams canceled in our other chapter. This is very similar to that copper example that we saw back there. Let's say though that we want to know how many molecules of water are in 10 grams. So if we want to do a problem like that, we would use both of these conversions. We would just say, well, if we know that it's this many moles, we would just do a second step and say, in 1 mole is 6.02 times 10 to the 23rd molecules of anything, water included. So then we have to use our calculator to take that answer, multiply it by 6.02, second, x to the 1 to give us scientific notation, 23rd power, and we get 3.3 times 10 to the 23rd, which is about half a mole, roughly. So molecules of water there. So that's how we use these definitions up here, whether it be Avogadro's number or grams for molar mass. Another kind of problem you might see would be if we have a calculation of how much, so stoichiometry of how much hydrogen is required to make 10 grams of water. So this is the toughest problems, and these are going to be the ones that you see in groups together. Notice the ratio here is 2 to 1 to 2. So if you wanted to make 4 moles of water, you could just use that relationship and not do any kind of calculations. You could just repeat the pattern. If this is 2 and this is a 4, this would be a 2, this would be a 4. If this was a 10, this could be a 5, and this could be a 10. So as long as you repeat the pattern, you can use any numbers, and that's the fastest way to convert moles to moles. Just use the pattern as long as the numbers are simple, and go that route. However, if they're grams, a little bit tougher of a problem. So if we're in grams, we're going to have to convert to, say, grams of hydrogen gas. So 10 grams of water, cancel, grams of water, we did that a moment ago. That was 18.02 on the periodic table. That was H plus O added up. That's per 1 mole. That's again using this definition here. Notice grams cancel. So if we want moles of water to cancel, we need moles of water to cancel down here. Moles of hydrogen gas would be what we want. This is where we use the mole ratio of 2 to 2. So every 2 H2s will produce 2 waters. That's using this definition. Lastly, what you're going to see in this chapter is moles of hydrogen going away. 1 mole is grams of hydrogen on the periodic table. That would be 2.02. That would be H plus H. All of that is your toughest kind of problem in this chapter. 10 grams divided by 18.02 grams times 2 divided by 2, wasted some time, times 2.02, and we get 1.1 grams of hydrogen. So in that situation there, notice what we did is canceled units, canceled units, canceled units. So this pattern is going to be very common over the next several weeks. If you have moles, little guy runs across the top, he gets scared, he goes underneath all the time. The reason this works is because these moles cancel. So if this is grams of A, this will be grams of A. This will be 1 because you're going to use the periodic table here. This is going to be the same thing, so these numbers are going to come from the balanced chemical equation, so this is the mole ratio. If this is grams of B, this will be grams of B, that'll be from the periodic table for something else. And this is how you can solve any problem from grams to grams. The only thing that's going to change is next week we're going to use milliliters. And this will be milliliters, and this will be capital M. And this can either be grams or capital M, which is concentration, using milliliters. So sometimes we're going to use milliliters in the same position, but it's going to be the exact same problem, just solved a little bit different. But that setup is very common, where you have grams here, and you have grams here. This chapter, and that comes from the periodic table, and you'll see that all the time. And that's your toughest kind of stoichiometry problem to deal with. We'll come back for some molecular formula kinds of problems.